All right, so our next topic is going to be 5.1 quadratic functions. This is the first section in our next unit, which is going to be quadratic and polynomial functions. So just a quick review, quadratic function, something of the form, standard form, y equals ax squared plus bx plus c, such that a cannot equal 0. If a is 0, then we no longer have a quadratic, we have a linear function. And we also have vertex form, and the simplified version here is y equals a times quantity x minus h squared plus k, where the vertex occurs at hk. It is possible that we actually have some quantity bx minus h, then the vertex would be at the quantity h over b comma k, all right? But I just put the simplified version here. Another thing to remember that's going to be very helpful in this unit is the vertex formula. All right, so given an equation in or standard form of a quadratic, ax squared plus bx plus c, then a vertex is going to occur at an x coordinate of the opposite of b over 2a and the y coordinate of f of negative b over 2a. So you're simply going to plug that x coordinate that you found back in, and you're going to solve or simplify for the y value. So one of the first things we should be able to do here is write the equation of a parabola given either a vertex and a point, or also it is possible that given 3 points, we can substitute in for x and y and come up with a system of 3 equations and 3 unknowns. Although I don't actually have that example in here because it doesn't pop up in the book in this section, but that's something else that we should be able to do as well. All right, so in vertex form, given a vertex of 2, negative 3, so h and k, that passes through the point 5, negative 1, so these would be my x and y points. So if we take a look at our vertex form, right, we have y equals a times quantity x minus h squared plus k. And I simply want to substitute in here, all right? When I substitute in for x, y, h, and k, I'm going to have the following. I'm going to have negative 1 equals some value a that I don't know yet times x minus, x is 5. So 5 minus 2 quantity squared plus the negative 3 for k. So I want to solve for a. So first thing I need to do is add 3 to both sides. I'm going to have 2 equals a times, and 5 minus 2 is 3 squared. 3 squared is 9, and if I divide both sides by 9, I get that a equals 2/9. So now that I know my vertex and my a value, I can substitute back into my vertex form of the equation, replacing a, h, and k, and I get the equation y equals 2/9 times x minus 2 quantity squared and minus 3. So what I had was a vertex at 2, negative 3 that passed through the point 5, negative 1. And I also know from symmetry that then this graph also has to pass through the point negative 1, negative 1. Right? So I've got a graph then that's going to look something like this. Okay? And for this purpose, that's a good enough sketch. It gives me the points that I absolutely knew. We could go through and plot a couple more, but for the purpose of what we're doing here, that graph is going to be good enough. The main thing was we wanted to find this actual equation. Okay. So just a little bit of a review with graph shifting. So again, I would be starting quadratic with parent function 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. So give me some kind of an equation. It's going to look something about like this. Okay, and I want to then shift this equation based on my graph, right, by graph shifting. So here, let's identify a few things. A equals negative 1/2. V is going to equal 3, 4. Remember, inside is opposite. Okay, so I want to now graph y equals a times the y values. Okay, I want to do that vertical stretch or compression. So 0 is still going to be 0. My 1s are going to become -1/2, and my 4s are going to become -2s, right? And if I were to, I would have 3/9 and -3/9. These would become 4.5. So I would have points here and here. I don't need those necessarily. I'm just putting them in for illustration purposes, so that I have a better picture of my graph. Okay, now I want to shift this entire graph 3 units to the right and up 4 units. So if I were to grab this whole thing and I make a duplicate of it, all right, I'm going to take this graph and I'm going to move it 3 units to the right and then up 4. Right, so if I were to take all those points individually and move them 3 units to the right and up 4, this is the graph that I would get for that final equation right here. Right? So remember, 3-step process: parent function, multiply all your y coordinates by a, and then shift your stretched or compressed graph according to the vertex. Okay, so let's say I have something that is in standard form. All right, I have 2 options. I can either complete the square or I can use the vertex formula. Here I'm going to complete the square because a is 1. It's going to be relatively straightforward. Okay, so here I'm going to have y equals x squared minus 2x plus some blank minus the 8 and then minus this blank. Because whatever I add here, I need to subtract it away here, right? It's that sleight of hand. And my entire purpose is that I want to figure out, based on my terms that contain x, what value or what quantity is going to complete the square and put this into vertex form. So on 1/2 of my b term, -2, so I'm going to have -1 squared, and I'm going to add it in both of these, or I'm going to add it here and subtract it rather, right? -1 squared is going to be a +1. Right? So what I end up with here is y equals the quantity x minus 1 squared minus 9. So a is 1, and my vertex, again, inside is opposite, so +1 and -1. So here, because my a value is simply 1, I'm going to graph the final graph. I'm going to be at 1, -9, right? I'm going to go over 1, up 1, over 2, and up 4, right? And if I went over 3 and up 9, I would have points here and here as well. Okay? So we're going to end up with a graph that's going to look something like this. Right? 1 or 2 things to note, right? When I have an equation in standard form, the constant of that equation, right, as long as it is in standard form and only in standard form, is my y-intercept. Okay, and here, because we're in standard form, I know that I should have a y-intercept at -8. When I graph this, I do in fact end up with a y-intercept, or I'm crossing that axis at -8. Right? Let's take a look at the next example. I have y equals -2x squared plus 6x and -8. Now, I could complete the square here, right? And I'm not going to do it, but let me set it up as if I were going to. I would have to factor a -2 out of these first 2 terms. So I would have -2 times x squared minus 3x plus some blank minus 8. And then I would have to subtract away this value that I'm adding. But remember, this value that I'm adding is also multiplied by -2. So when I subtract this away, I'm really going to have -2 times whatever that blank is. Okay, so I can do it this way, and it's not going to be incorrect. I would have to find 1/2 of -3, square it, and add it to both places here. You're more than welcome to do that, or you can use that vertex formula. So the vertex formula, right, I know here a is -2. It's going to be -2 regardless. Okay, so when I complete the square, or when I use that vertex formula, a is still going to be -2. So I'm going to have the opposite of b over 2 times a, right? So here I'm going to have -6 over -4 or +3/2. When I plug that in for y, I'm going to have y equals -2 times 3/2 squared plus 6 times 3/2 and minus 8. So 3/2 squared is going to be 9/4. 9/4 times -2 is going to be -9/2, right? 2/3, or excuse me, 3/2 times 2, excuse me, is going to give me, I'm going to reduce here, 6 divided by 2 is going to give me a 3, 3 times 3 is 9, but I also need a common denominator. So I'm really going to have 18/2. So actually reducing here was kind of pointless because I just undid it when I made a common denominator. And then the -8, I need a common denominator of 2, so we're going to have -16/2. Right? So when I combine like terms here then, I'm going to get a y value that is going to be, let's see, -7/2. So I now know h, I know k, and I already knew a from above. So my equation here then is going to end up being y equals -2 times x minus 3/2 squared and minus 7/2. So I'm going to end up with a graph at +3/2, so 1.5, and -3.5. So I'm going to be right here with an a value of -2. So it's going to open downward. So I'm going to go over 2, or over 1 and down 2. Right? And over 4, or over 2, and instead of down 4, I'm going to go down 8, which is going to put me down here around 11.5. Okay? I know that I should have a y-intercept at -8, so I should go through this point here as well. Right? Gives me one more point of reference as that graph. And I also then know that I have to go through a point here as well based on symmetry. So I get a graph that should look something about like this. Again, I could have found, and once I would have simplified, -3/2 squared and the 9/4 that gave me, this would have given me that as well. Or I could have found the a, the h, and the k like we did and substituted those into the vertex form of my graph. Right? So a quick little theorem here, right, on max or mins of a quadratic function. If I have a quadratic in standard form, then f of -b over 2a, so the y value of the vertex, is a maximum of the graph if a is less than 0. Think about it, if a is less than 0, I'm going to have a graph that opens downward, right, and that vertex is going to be the max of my graph. If a is greater than 0, then it's going to be a minimum of the graph. I'm going to have a parabola that's opening upward here, and that vertex is going to be the lowest point, or the minimum of the graph. All right, so max and mins are going to come up a good bit in applications of quadratics. There are a lot of different uses for applications and word problems with quadratic functions. They model a lot of things very nicely, not only in physical applications, but also sometimes in business applications as well, and a few other places. Okay, so the primary things that when we're dealing with quadratic functions that we're going to be asked to do is, given one variable or the value of one variable, find the other. Okay, so we could be given x and asked to find y, or given a particular y value, go back and solve for and find the x values that make it true. Or we could be asked to find a max or a min of the function. Right? If you're asked to find a max or a min, as soon as you see max or min, that should be a red strobe light that's saying find the vertex of the function. Okay, not sure how I just made that shape. All right, so max or min, you're going to find the vertex. If you're given x and asked to solve for y, just plug in and solve appropriately. Okay, the quadratic formula is going to come up and be something that's going to be useful to us here again as well. So x equals the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. All right, if somehow you don't have that committed to memory at this point in time, you should probably do that going forward. We're going to be using that in this section and also as we move into polynomial functions over the next couple of days as well. So let's do a max or min example here. All right, so I don't know if you've ever seen the videos of, who I think are a little bit crazy, and I'm an adrenaline person myself, that go down to Acapulco, Mexico, and they actually jump off of the cliffs into this cove and they dive in, right? Some of those cliffs are pretty high, right? So let's model this here. All right, so I've got a cliff diver, right, starting at a height of 80 feet above the water. And he's going to jump, and he's going to have an initial upward velocity of 15 feet per second, okay, a vertical velocity, all right? Now, granted, he's jumping out, hopefully, all right, as well, but the only part of this velocity that matters is the vertical component of his velocity. So if he's jumping out, if the vertical component is 15 feet per second, his actual total velocity, or his net velocity, or the vector on which he's jumping, his actual magnitude or velocity in that direction is greater than 15, okay, because it has to then account for not only the vertical but also horizontal component. Again, here we're only concerned with the vertical component, okay. So we're going to have our cliff diver, right? He's going to be standing on my cliff, okay, and he's going to be jumping into the ocean below, right? And since I'm a phenomenal artist, right, we're going to have our guy, I don't know, let's make him, maybe he's an alien, okay, because who's actually crazy enough to do this, right? And he's going to jump up, right, at some initial velocity and down into the water here, okay? So, again, we're looking at the actual vertical velocity of this particular jump, right? His initial vertical velocity is 15 feet per second, right? The downward acceleration due to gravity is negative 16 feet per second squared, okay? If we're dealing with in terms of meters, it's going to end up being negative 9.8 meters per second squared, okay? And he is 80 feet above the water. Okay, so I want to find what his maximum height is, right? If I'm finding the maximum height, right, I'm finding the actual y coordinate of the vertex. And the second part says, when is he at the max, all right? So really, the second part of the equation I have to answer before I can even get to the first part, right? So let's find the x, or let's actually use the variables of the equation, the t value, my input or my domain value for the max, right? So I'm going to have the opposite of b over 2 times a. Right? When I go and do this, I'm going to have negative 15 divided by negative 32, or I'm going to have 15 30 seconds. Right? If I come up with a decimal approximation, which is probably more appropriate here, I have 15 30 seconds of a second. So we have at 0.46, let's do 469 seconds, we're going to be at a max. Okay. Then for the h component, so I want h of 0.469, right? And I'm going to substitute that in, I'm going to evaluate. So I have negative 16 times 0.469 quantity squared, plus 15 times 0.469, plus 80, and I'm going to get that he has a maximum height of 43.516, if I round, feet. Okay? So this guy's got a vertical leap of 3.5 feet. All right, he should probably be playing some pretty high level volleyball, or maybe playing some basketball somewhere. All right. But our diver has a max height of 83, and we'll just round to nearest half foot, 83.5 feet at 0.469 seconds. Okay. The one thing that's going to be somewhat up to interpretation here, right? We're not going to count significant figures and figure out how many we should have like you might do in science class. What I'm going to say there is if you have any doubt as to should I round to 1, should I round to 2 or 3 decimal places, I would rather you round to too precise of a decimal approximation than not precise enough. So if there's any doubt, use an extra significant figure, an extra decimal place for your particular answer. Okay, so let's come down to the next part here, right? It says our cliff diver, same equation. At what time does our diver hit the water? So if we take a look here, when he hits the water, right down here, okay, the height of my diver is 0 feet. So it doesn't necessarily say set h equal to 0 and solve for t, but in the context of the problem, that's what we're being asked to do. So here I'm going to have 0 equals negative 16 t squared plus 15 t and plus 80. Okay? Excuse me. I can look here and try and find a GCF. There isn't one, all right? At least nothing that's going to make it nice and easy. I can go through and attempt to solve this, a times c, and see if it factors. But in all honesty, let's see, 80 times 16, factors of negative 1280. I don't know them off the top of my head, and I'm not even 100% certain that there's going to be one that exactly equals 15. So let's make our life easy. Let's just use quadratic formula. So t is going to equal negative 15 plus or minus the square root of 15 squared minus 4 times negative 16 times 80, all divided by 2 times negative 16. Okay. We can go through and simplify that. I'm going to use the quadratic formula just for the sake of speed here. All right, so I'm going to find quadratic formula. I'm going to hit enter, and it's going to ask me for my a value, which is negative 16. Again, make sure you're using that negative key and not the minus. 15 and 80. And this is going to point out my quadratic formula. And if I click on it here, it's going to actually give me the max, again, that we found earlier of 0.46875 and 83.515. Now, if you look down at the bottom, I get two values for t. I get t equals negative 1.82 seconds, and t equals 2.75 seconds. Now, if we think about it, the negative 1.82 seconds would be back here on the left, right? So assuming that this motion, right, from the point where he jumps into the water would have been a continuous and starting from the water and following this parabolic path, right, we would get that other solution. In this case, this one makes absolutely no sense. I can't hit the water before I jumped. So the only one that really makes sense for us here is t equals 2.75 seconds, and our cliff diver enters the water 2.75 seconds after he jumped, okay? So the next one we're going to take a look at is an area example. All right, so let me get rid of my graphing calculator for the moment so I have a little bit more room to work here. So a farmer wishes to put a fence around a rectangular field and then divide the field into 3 rectangular plots by placing 2 fences parallel to one of the sides. If the farmer can only afford 3,000 feet of fencing, what dimensions will give the maximum area? Okay, so I'm going to have a rectangular field here. Okay, gave me a square. Let's try that again. So I want a rectangular field. Oh, it gave me a square again. All right, so now I got a rectangular field, and I'm going to divide this up into a couple of plots, and I'm going to make them be pretty close to equal. Okay, so we're going to assume that they're nice and evenly spaced. I want to do this in the simplest way possible, right? So I'm going to use a length and the width here. And I'm going to use the length for the entire length of the total area, because then I only have two lengths. And I'm going to use the width for the entire width of the area, all right? And it's going to make life a little bit easier. Now, if I switch colors, okay, and for the width, I'm going to have then 4 total widths of fence. I could break this up, and if I use X's and Y's, I could do X's, right, and Y's, right, and break this into all of the components for this fence, right? But the problem is, this is going to get pretty messy in terms of the values that I'm going to be dealing with. So instead of doing that, I'm going to keep this as easy as possible, all right? It's not wrong the other way. You're just going to deal with some crazy fractions and values that are going to get messy. So my area is simply going to be length times width. I have a total amount of fencing of 3,000 feet, and it's going to be described by 2L plus 4W. What I've got here is a system of equations. And right now it's not a quadratic, but I'm going to make it into a quadratic. Right? So I'm going to solve this equation for one of my two variables. It really doesn't matter which one I solve for, but I want to solve for a value that's going to make my life easy and preferably without fractions. So here I'm going to solve for L. L is going to be the simplest. When I solve for L, I'm going to have the following. I'm going to have I'm going to have 1,500 minus 2W. I'm going to substitute that in, replacing L in my area equation, right? So I'm going to have area equals, we're going to have 1,500 minus 2W times W, or when I put this into standard form, I'm going to have negative 2W squared plus 1,500 W. Now I have an equation that is in standard form. Consider the vertex, though, also is going to be my width and my area. Okay. I intentionally didn't use X and Y here because it's very possible that when I solve here that I could have ended up with an independent variable that would have been the Y value. So in the X position, you would have actually had the Y variable. So I intentionally avoided X and Y just to alleviate some confusion. So let's find my input, or my W dimension. So it's going to be the opposite of B over 2 times A. 1,500 divided by 4 is going to come out to 375 feet. The area dimension then is going to be negative 2 times 375 squared plus 1,500 times 375. So if I plug this into my calculator, all right, negative 2 times 375 squared plus 1,500 times 375, I'm going to get an area of 281,250 feet. I'm just looking to make sure that that makes sense. I feel like that's a little large. For the moment, I'm going to go with that, although I feel like that number is a little bit big, right? And I'm trying to see if I made some kind of a silly mistake somewhere in my work. All right, I don't see a mistake right now, right? And I think we're good to go here. Yeah, it sounds about right. There's like 640 acres per square mile, and each acre is 43,500 square feet, I believe. So no, that value does sound right. Okay, so we have a max area of the 281,250 square feet. I have a width dimension of 375. And if I come back to my equation here where I solve for the other variable, I want to use that, and I'm going to substitute in L equals 1,500 minus 2 times my W of 375. So 1,500 minus 2 times 375. And we're going to get a length of 750 feet. So the dimensions for max area are going to be 375 by 750. And those units are feet. Now the one thing, if you go back and look at the question here, I only was asked to find the dimensions that give me the max area. So I never really actually had to find the max area itself, okay? This gives me, again, the dimensions of my width of 375 by my length of 750. If I were asked to find the dimensions of each pen, I would then have to go through and divide this length by 3, and I would get that each pen is going to be 375 feet by 250 feet. All right, so pay attention exactly to what you're being asked to find. Make sure that you're answering the question completely. I have answered it here. There's nothing else that I need to find. Okay. Let's just come back down to our next example. So I have another application of quadratics, and here I'm doing something from a graphic. Okay, so let's say I've got a basketball player shooting maybe a free throw. Okay, and I have a path of the basketball after the shot mapped on to an XY axis from the point at which it was shot. Now, I did put my XY axes here in red so that it's easier for us to see. So I'm going to switch to like a bright pink just so it's easier to see. So the ball is going to leave our shooter's hand here at the origin. In a problem like this, you want to orient your axes such that ideally, if you can, put 0, 0 as one of your important points. It's going to make your life at least a little bit easier. All right? And we're going to assume that this is the max of the basketball, right? Excuse me. Should probably have another basketball here that shows that it's now coming back down. All right? So what I need to do is figure out what is the equation, or what are the coordinates, rather, of this vertex, so I can come up with the equation for my path of the basketball. So here, we're going to be at -4, according to the grid, and 7. So -4, 7, and I'm going to have the point 0, 0, through which is also going to be a point on my graph. So we're going to substitute into y equals a times x minus h, quantity squared, plus k. Because what I want to do is I want to figure out, does the path of my basketball come down, and do I make the shot or not? Right? We can look at it and, we can make a guess and say, well, kind of looks like hopefully it should, maybe it won't. But it's going to be close. I need an equation to figure that out. So I need to know, right, and we're going to assume that the rim of my basketball is right here. and it goes essentially from -7.3 through -8.3. So I just need my basketball in its y value to cross 3 between -7 and -8. Okay. All right, for us to go in. Now, obviously a basketball could bounce off the rim and bounce out. We're going to assume that if the basketball passes through there, that it's going in, it's not going to bounce out. Okay. So let's do a little bit of math here. So we're going to have y0 equals a times 0 minus -4 squared and plus 7. So if I want to solve for a, I'm going to end up with a -7 equals a times 16, or a equals -7/16. Okay. My vertex I know, so I'm going to have an equation of y equals -7/16 times x plus 4, quantity squared, and plus 7. Now again, I want to know, and there are a couple of ways I could go about this. I want to know between -7 and -8, does my ball pass through the point, or the y value, 3. Okay? Or I could substitute in the y value of 3 and solve for the x's and figure out exactly where we cross. All right? And let's do that. Okay? So I want to substitute in 3 equal to -7/16 times, right? And an x plus 4, and I'm going to multiply that out. So I'm going to have x squared plus 8x plus 16 plus 7. All right. I'm going to try and solve this, so let's do a little bit of simplification here. So I'm going to have 3 equals -7/16 x squared minus 56/16 x minus 7 plus 7. All right, so if I simplify, then we're going to have -7/16 x squared minus 56/16 x and minus 3. Okay, again, I'm just going to go straight to the quadratic formula. It's going to make my life easier. I don't want to try and actually factor and solve that. It's going to be pretty messy. Okay, so let's go back. Let's run my quadratic formula program a second time here. All right, so A is going to be -7/16. B is -56/16. And C is -3. So I'm going to get solutions of x equals -7.02 and x equals -0.976. Okay. Now we did say over here that from -7 through -8 is when we cross. So our basketball is just barely going to make it in inside of that rim. Okay. Now, again, we could argue here, and I think last year we actually had the conversation that that basketball might hit that front rim and bounce out. But for the context of the problem, right, and you could make that argument, and it wouldn't be wrong. Okay, but for the purely mathematical argument, we're going to say that that ball crosses y equals 3 within that range of -7 through -8. So yes, the shooter makes the shot. Now, again, I agree that we can make an argument that maybe it bounces off the rim and bricks out. Maybe it bounces off the rim, hits the backboard, and goes in. All right. But again, we're going to simplify it, and we're going to say that it fell within that range of values and that the shot is good. Okay. That's all I've got for 5.1. You're going to see some application of quadratics problems. And I've got an application of quadratics worksheet that you guys are going to work through in class tomorrow. right? So take a look at a few things, maybe take a look at a couple of the problems from the stacks assignment in the book and just try a couple. And then we will focus most of our attention on, pardon me, application problems tomorrow in class.